Welcome. This is the fifth video in the series on principles of radiographic exposure. Last video we discussed X-rays and their interactions with matter, attenuation, and differential absorption. In this video we will explore radiographic image properties. We'll start by looking at matrix and pixels. Digital images are composed of numerical data. This numerical data is placed in a grid made of rows and columns. This grid is referred to as a matrix. We can see the matrix right here. So a column is up and down like this, and rows are like this. Each grid element is called a pixel. So this is one grid element right here. This would be referred to as a pixel. The matrix is measured by the number of pixels on each side of it. An example, we like 1280 by 720. Okay, this one in the example here is like a 2 by 2. There's 2 pixels going this way, and there's 2 pixels going this way. In other words, there's 2 rows and there's 2 columns. The length of the image is referred to as the field of view. So if like 10 by 8, this could be in inches. Okay, it could be measured in any length, centimeters or anything. However, so if this was like 10 inches long one way and 8 inches long the other way. So now that we introduced the concept of field of view and pixel size, what they are, we'll go ahead and we'll talk about the relationship between them. The field of view and the pixel size are related by the equation pixel size equals field of view divided by matrix. This equation here indicates that as the matrix gets larger, as it becomes a greater number, the pixel size will get smaller if the field of view stays the same. It also says that if the matrix is decreased, the pixel size will get larger. Okay, so if the matrix becomes less, okay, so like there's less pixels across, and the field of view stays the same, then the pixel size must be larger. Also, in this equation, what we can infer from it is that if the field of view increases, the pixel size will increase. When the matrix size is stagnant. And if the field of view decreases, the pixel size will get smaller, okay, without the matrix size changing. So now we'll go ahead and we'll talk about another quality that describes the matrix and pixels. It's called pixel pitch. Pixel pitch is the distance from one center of a pixel to the center of the next pixel. It indicates how close the pixels are together, and it describes the pixel density. Another one is pixels per inch. It could also be described as another closely related measurement to pixel pitch. Pixels per inch is just that, how many pixels there are in an inch of an image. The greater the pixels per inch, the more pixels per inch the image will have. Okay, so the larger the number, the more pixels there are in every inch. This means that the image can be viewed closer compared to a lower pixels per inch image. An example of pixels per inch of a phone could be like 458, okay, and an HD TV could be 92. So a phone is meant to be viewed much closer, so the pixels are much closer together, so when you are closer to it, it's much more crisp to look at, you know. And then the HD TV you're meant to view from a distance, okay, and so the pixels per inch aren't as high. Recommended viewing distance is dependent on pixels per inch, okay, and we have a little example here of 24-inch televisions here, okay, and it has the resolution of them, and then it has the pixel density. So like at 92 pixels per inch, the optimum viewing distance is 37 inches, and then as it goes up on the same TV, same size, so the same field of view here, 184 pixels per inch on this example, and it can be viewed about 19 inches away, so you can be closer with a higher pixels per inch density. For radiologists, their screens are designed for viewing from common distances that they may be away from the monitor, okay. So a radiologist's screen is designed in a certain way with a certain pixels per inch, where the viewing distances are such that they're going to be they're going to be sitting a certain distance away, okay, from it. And then your phone is designed to be viewed from just a few inches away. So the phone, example, like 458 pixels per inch, you know, as it goes up here, it's a closer distance. So your phone's meant to be viewed very closely. Now that we talked about those ideas of the matrix, the field of view, the pixel pitch, the pixel size, let's go ahead and visualize it here. So we'll start with the matrix. So the matrix of this example right here is like 2 by 2. So there's 2 pixels going this way and 2 pixels going this way. Okay, 2 rows, 2 columns of pixels. Something like the field of view. So the field of view, so this could be like 4 inches this way. This could be like 4 inches that way. Okay. The pixels per inch, if this was the case, if this was 4 inches and it was a 2 by 2, would be 0.5. So there'd be a half a pixel per inch, okay? Because it would be 2 inches for this one pixel, 2 inches for that, and so inverse that. So per inch would be a half a pixel per inch in this example. All right. So the pixel size is just the measurement here, okay? It's not the measurement like across this way or anything. It could be like this, and the pixel size doesn't have to be even, okay? So if this was a 2 by 2 matrix and this was 6 inches, okay, and this was 4 inches, then the pixels would be square, and that happens, okay, sometimes for different scaling and everything. So so the pixel size could be one this way and one that way, all right? But here they're just squares, so the pixel size could just be measured with one size, and this is the pixel pitch, okay? From the center of one to the center of the other, all right, is this distance, and that's called the pixel pitch. Now let's talk about image properties. Okay, we discussed about matrix and properties that go into that. Let's talk about some image properties. So there's 2 main classifications when discussing image properties. They are sharpness and visibility. Sharpness can be further divided into 2 categories called spatial resolution and distortion. Visibility can be divided into contrast and brightness. Okay, so we're talking about an image, right? So an image has sharpness and visibility. Some of the ways we look at these things is by looking at the spatial resolution, okay, that goes with sharpness, and also the distortion. And visibility, brightness, and contrast are the 2 parameters that we're worried about here, or that we're going to look at, okay? And these 2 ideas, the visibility and the sharpness, can be interrelated, okay? So we'll go ahead and we'll talk about sharpness of the image, okay? And as we can see here, this image is pretty sharp. We can see some meshing in here, okay? So we can really see these fine lines, okay? And well, let's talk about what that can mean for what we're visualizing here. So when we talk about sharpness, we'll go ahead and we'll start by talking about spatial resolution. Resolution is the ability to render objects on the screen or on the image. Spatial resolution is a radiographic image. In a radiographic image is the size of an object the system can visualize. So the spatial resolution is the size of the object the system can visualize. Most people could see objects as small as about 200 micrometers. Some people can see smaller, okay? So they can see maybe 100 or maybe even 50 micrometers down. The greater the resolution, the smaller the object the system can display. So if the system has greater resolution, it can display smaller objects. The resolution of the system is related to the pixel size, okay? So the greater the pixel, the smaller the pixel size, the greater the resolution, okay? The greater the pixel density, also the greater the resolution, okay? That's like the pixels per inch, like, okay? So if we look here at this picture, okay, we can count this matrix down here in the bottom right. These are all the same picture, okay? So this matrix is 1, 2, 3, 4, and it's roughly 2, 2 and a little extra, okay? So it's 4 by 2. So we can't really see many objects here, right? Okay, it's very blurry. We just have some grays, all right? So we add some, and now we can start to see some structure in things, but we can't really make out any objects here. In this picture, we have more pixels per inch, so there's more pixels lined up, okay, per every inch of this viewing here. So the resolution's better, we would say here. We can start to make out some objects here like this, and this is kind of a line here, and all these structures here, right? And then we move up to a much higher resolution, okay? And now we can visualize much more, okay? So the greater the resolution, the smaller the object the system can display. So there's very small details in here, all right? The resolution of this one's greater, so we can display it. Spatial frequency. In medical imaging, spatial resolution is measured in spatial frequency. Okay, so when we're talking about the resolution, the spatial resolution of an image, we're going to give the quantity, it's going to be the spatial frequency of the image. Okay, so spatial frequency quantifies how closely lines can be to each other and still be visibly resolved. So how close two lines can be to each other and still be able to be seen individually. Spatial frequency is measured in line pairs per millimeter. How many of those lines, a pair of them, two of them, can be visibly done in every millimeter, okay? A line pair consists of a solid black line and a white line, both of equal widths. So this is one line pair we see below. So it's one solid black line, and then there's a white line, okay? So this would be one line pair, all right? And if this is, if this was 1 millimeter, okay, and that's the farthest down that we could see, that we could visibly resolve on the image, then the spatial frequency of the image would be one line pair per millimeter. Okay, we'll go ahead and we'll talk about that some more in the next slides. So it takes 2 pixels to display one line and 1 pixel to display the space. Okay, so therefore it takes 2 pixels to display a line pair and only 1 pixel to display a single line. Okay. One object can be displayed on 1 pixel. So since we can display a single line, okay, on a pixel, that could be an object. So an object could be a line. So a line can be seen on 1 pixel. But we need 2 pixels to see a line pair. Okay. With this, it can be concluded the smallest object a system can display is the size of 1 pixel. The typical spatial resolution of digital radiology systems is between 4 and 6, okay, line pairs per millimeter. The spatial resolution of a system, okay, so now we'll go ahead and we'll work through a couple problems here, all right? The spatial resolution of a system is 9 line pairs per millimeter. What is the smallest object the system can display? There are 9 line pairs per millimeter, and we need to find the size of one line, okay, because we're talking about the smallest object, okay. What we just learned about is that the smallest object the system can display is one line, okay, which is 1 pixel. So there are 9 line pairs, so there's 9 pairs of lines, so that's 18 individual lines per millimeter, and we need to find the size of one line, okay, in order to answer what's the smallest object the system can display. So the first thing we'll do is we'll go ahead and we'll say there's 9 line pairs, okay, and there's 2 lines for every line pair. So that means that there will be 18 lines or 18 objects per millimeter. All right, we can write it like this: 18 objects per millimeter. We need the measurement of in the size, okay? So right now we have 18 objects per millimeter, all right? So we need how many millimeters there is per object, okay? Millimeters per object. So we go ahead and we do the reciprocal of this, okay? Right now we just have 18, all right? And it could be like 18 over 1, and we go ahead and we do the reciprocal of that right here, okay? And then we get this number, the 0.0556 millimeters. A better way to write this would be in micrometers. So we go ahead and the difference between millimeters and micrometers is 10 to the negative 3 difference. This is 10 to the negative 3. This is 10 to the negative 6. So we go ahead and we move the decimal point over 1, 2, 3, and we get 55.6 micrometers. Okay, and typically it's going to be in micrometers because that's the size of pixels are typically in micrometers. The smallest objects that can be rendered on digital imaging is typically in the realm of micrometers. So the spatial resolution of a system is 4 line pairs per millimeter. What's the smallest object the system can display? Okay, so now we have a different question. There are 4 line pairs per millimeter, and first we need to find the size of one line. Okay, so we'll do the same kind of process here. All right, there's 4 line pairs per millimeter. We're going to multiply it by 2. Okay, and that's going to be 8 objects per millimeter. Okay, objects per millimeter. We can write it like this. Therefore, the smallest object the system can display will be the reciprocal of this, which will be millimeters per object. All right, and that is going to be the 0.125 millimeters. Okay, and when we switch that to micrometers, 125 micrometers. So for a 4 line pairs per millimeter system, it's 125 micrometers, whereas on the 9 line pairs per millimeter, it was the 55.6 micrometers. Okay, so the higher the spatial frequency, what we can take away from this, the higher the spatial frequency, where the first example was 9, this one's 4, so the first one was higher with 9 of the system, the higher the spatial resolution and the smaller the object the system can display. Okay, so this kind of makes sense. I mean, with a higher resolution, the frequency, the spatial frequency is higher, as we've learned what spatial frequency is. The smaller the object the system can display. So the one with 9 line pairs can display a 55 micrometer object, where this one can only display 125 micrometer object. Okay, with the 4 line pairs per millimeter. So now let's go ahead and talk about object size. Anatomical parts can be described by spatial frequency as well. Okay, so far we've talked about like the image having a spatial frequency, and we talked about how it relates to the size, okay, and how it can, and what the system's capable of, you know. And so the anatomical parts can be described by spatial frequency as well. A part with a high spatial frequency will be smaller. Okay, so just like we learned, the higher the spatial frequency, the smaller the object, or the smaller the system can visualize. Okay, so the same with the part. The higher the spatial frequency, the smaller the part with high spatial frequency will be smaller than a part with low spatial frequency. Okay, so a liver may be like a low spatial frequency part. Okay, let's say, while the vessels that are inside the liver, okay, would be like a high spatial frequency, okay, because the vessels are much smaller. All right. On an X-ray system can only image an object the size of 1 pixel, as we discussed. Therefore, if a part has a higher spatial frequency, so it's smaller essentially than a pixel, it is difficult or impossible for this system to represent. Okay, so if the vessel's inside, the spatial frequency is higher. Okay, so the part's smaller. The system can't represent that. Okay, it's not going to be able to visualize that. And if we go back to the images before, where there were the matrix, the different size matrix, where there was the 4x2, and then it kept adding more and more pixels, and it became sharper. Okay, so if we think about the resolution of that bottom right one, where it was just big chunky blocks of gray and black and white and everything, we couldn't represent very small objects on that one, right? Okay, even though what we were trying to image had a lot of small objects. Okay, we needed to have a appropriate spatial resolution of the image, like in the top left, in order to see, okay, those small objects. All right, because the spatial frequency of those objects was greater than what the system could represent. Okay, in the bottom right and in the bottom left images. Okay, so now all this is kind of relating pretty well here. So we'll go ahead and we'll talk about the object size, and will pose a question of a system can visualize an object as small as 100 micrometers. What is the spatial frequency of this system? 100 micrometers will be the size of one line. Okay, so we said that the smallest object the system can represent is one line, which is 1 pixel. So the smallest object the system can represent right here is 100 micrometers. So that means it's one line. It takes 2 lines to make a line pair. So we go ahead and we take the 100, we multiply by 2, so we know there's 200 micrometers per line pair. We convert the unit to millimeters because we need per millimeter. All right, so we have 0.2. This should be millimeters. So we have 0.2 millimeters. Then we take the reciprocal. All right, so we go ahead and we take the reciprocal of that, and we have 1.02, which equals 5. So 5 line pairs per millimeter, this should be millimeter, is the spatial frequency of the system. Okay, so if the system can visualize an object as small as 100 micrometers, then the spatial frequency is 5 line pairs per millimeter. Okay, is the spatial frequency of the system. So we'll go ahead now and we'll discuss the modulation transfer function. The measurement of a system's ability to represent anatomical parts of different sizes can be quantified with the modulation transfer function, or MTF. That's how we'll write it for short. So this sounds like a big fancy kind of term, and it kind of is, but at its root, it's just a measurement of the system's ability to represent anatomical parts of different sizes. Okay, so we talked about how different size parts can have different spatial frequency. All right, and the system also has a spatial frequency to it as well. So the modulation transfer function kind of brings these two ideas together of the size of the parts and then how well the system can visualize. Okay, the MTF is just a term adopted from radio. A system that can perfectly represent any size object, no matter how small it is, will have an MTF of 100 or 1. Okay, so if the system is perfectly representing an object, the MTF will be 1. Okay, and a system that can perfectly represent any size object, the system's MTF will be 1. The MTF of a system is typically about 10% or 0.1. Okay, so no system has an MTF of 1. All right, so this is an important thing to know. All right, about MTF, that no system can perfectly represent an object. Most systems have an MTF of about 0.1, and there's a curve that goes along with it. So we say the spatial resolution, okay, of the system, how well we can see. All right, and we take that MTF value, okay, right here, and then we when it falls off here, and then we take it and we draw it out. It's about 10%. Okay, so about the 10% mark, okay, is where we draw the line right here. Okay, and that's the limiting spatial resolution, okay, of the system. So this is the smallest that the system can represent. Okay, and this would be like as object size gets smaller. Okay, as object size gets smaller. All right. Then how well does the system represent it? Okay. We'll go ahead and we'll have some spatial resolution questions. All right. So we worked a couple before. There's a couple more here. All right. And go ahead and pause the video here if you need to. Go ahead and try to work them out based on what we've learned, and the answers will be later in the video. Now we'll move on to distortion. So we talked about the sharpness of an image, and we talked about spatial resolution and the spatial frequency and how that's represented on the image. And now we'll go ahead and we'll talk about distortion, which is the other aspect of sharpness. Distortion is a misrepresentation of either the size or the shape of the anatomical part. So there can be size or shape distortion. Size distortion is due to magnification of the part as a whole or an area of the part. Shape distortion is due to the part being unevenly magnified or improper positioning. In order to understand distortion, we got to talk about distance. The distance that objects are away from each other will change the size that the object appears. So if we're far from an object, it won't appear as big or as large as if we're really close to the objects. Okay, we know this, but in radiology there are a few distances that are of importance. They are the source to object distance, which is the SOD, the source to image distance, which is the SID, and the object to the image distance, which is the OID. The source is the source of the x-rays, so the target spot on the anode is the source in radiology. The object is what is being x-rayed, typically the patient. If it's a patient, it's the anatomy of the patient. So it doesn't just have to be the patient itself, it can be like the heart, okay, or it could be a specific bone, or things like that, okay. The image is where the image is going to be created, so the detector or the IR, okay, is the image. We'll go ahead on this one and we'll visualize what we're talking about here, okay. So the source is the target spot, okay. So this is the source, this is where the x-rays are created, and at the target spot of the anode, alright. So the source, as we discussed, the source is here to the image distance, okay. The image is going to be created at the IR here. So this is a source to the image distance, alright. The source to the object distance, the source is the target of the anode, all the way to the object. It could be like inside the body here, maybe in this area it's gallbladder, kidney-ish, maybe, alright, or whatever the structure might be in the body, okay, is the object. So the source to the object distance is this, and then from the object to the image, okay, is this orange distance here. Alright, so these are the different distances that we're describing. The equations relating to the distance are as followed, okay. So the SID equals the SOD minus the OID, okay, or plus the OID. So the source to object distance from the last slide plus the object to image distance equals the SID, okay. And from this we can derive these other equations, okay. So if we just take away the OID, the object to the image distance, away from the total distance of the SID, right, we'll get the source to object distance, and the OID works the same way, okay, but we take away the source to object distance. So so these are some important relationships, you know, just to have, but this is really the only one that you need to know, and then you can find these other ones from it. Distortion, and we'll talk about magnification, okay. The magnification of a part is due to the distance the source is from the image receptor. Alright, so the magnification of the part is due to the distance the source is away from the image receptor and how far the source is from the object. Alright, so since there is always a length, the object will be away from the IR, okay, so no matter what you're imaging, there's always going to be some distance away from the IR, even if you put them right up against it, okay, due to the thickness of the part, due to the part being 3D, the thickness of the part, even if it's the hand, and we're doing it PA, the posterior portion of the hand, okay, is going to be some distance away from the IR, okay, so there's going to be some object distance always. So there will always be some kind of magnification. All right. The amount of magnification present is called the magnification factor, which is this MF that we use. The equation for the magnification factor is the SID over SOD. Okay, so this is kind of a common way to say it, SID over SOD. Okay, and that's an easy way to remember it. So the relationship of how far away the source to the images, and then how far the source to the object distance is, okay, represents the magnification. So we'll go ahead and we'll continue talking about magnification. A radiographer's goal is to display the anatomy as true as possible. Therefore, magnification needs to be reduced as much as possible. All right. When we increase the magnification, we're not truly representing the part that's being imaged. In some cases, magnification may be desired. All right. In some instances, but for the most part, we don't want to. We want to minimize magnification on certain projections. The part of interest cannot be placed as close to the IR, therefore OID is increased, making the SOD smaller. Okay, so in certain projections we can't quite get the part as close, so to lessen the magnification factor, the SID is increased. All right, this is why unlike lateral C or T spines, where we can't, because of the shoulder and everything, we're not going to be, the part of interest, which is the spine, isn't going to be as close to the image receptor when we're in the lateral position, when the patient's in the lateral position, and so the SID is increased, okay, to reduce this magnification factor. It's increased typically to 72 we would use, when other images are at a closer distance, right? So with the APs and stuff, we move into the closer distance, okay? So that's the reason why we use the longer SID on those projections. We'll go ahead and we'll continue talking about magnification and distortion. In a radiograph, not all the anatomy on the image is going to be magnified the same amount. This is due to the location of the part in what is being x-rayed being farther away from the image than other structures, other anatomy. Okay, and we can see that right here, how this one's farther away than this one. This is why we perform the chest x-ray PA. So we perform it PA so that the heart is closer to the IR, right? Okay, and it can be better represented, and that in a T-spine AP, so the spine is closer to the IR. So here we have this the magnification factor again. I took these lines measured in pixels. Okay, so I measured how many pixels each one of these was for this one here, where the part's farther away. I got these values, so I determined that the magnification factor is 1.35, and on this one here, where the part is closer to the IR inside the body, that the magnification factor is 1.13. Okay, so this part's going to be better represented, it's going to be less magnified, okay, than this part. And the more magnified the part is, okay, on this projection down here, the more pixels it's going to take up, so the more blurry it's going to be. It's not going to be quite as sharp looking, okay? It's going to be a little more fuzzy. All right, we call the fuzziness, we call it penumbra. Okay, so penumbra is a term that might come up, and we call that a fuzziness, and we call, when it's clear on an image, we call that umbra. All right, well, we'll talk more about this later, but penumbra is typically a term that can be used for blurriness. All right, so from this we can conclude that the thicker the part, the more distortion is going to occur. Okay, so the more thick, because there's more structures in here that are going to be more magnified. Okay, where if the part's just really thin, like the part's only from here to here, okay, it can only have this much of a variance, okay, in the magnification. So continuing on, magnification can also be different throughout the image due to the divergence of the beam. Okay, the anatomy at the outer edges of the image can be more magnified than in the center. This is why the central ray is on the central part of the interest. Okay, the effect of this is really minimal. Okay, the effect is greater when the SID is shorter and the field of view is larger. Okay, but overall this effect is minimal. Okay, this topic will be further discussed in the advanced topics of radiology playlist. But we can see here that this would be like the central ray. Okay, so this is the distance of the central ray, and then this would be the SOD of that. Okay, and we can see that this SID is longer. Okay, for these two, the one on the left represents this one, the one on the right represents this one, and the SOD is longer too. Okay, and as I said, there'll be more advanced videos on this in the advanced topics of radiology playlist. Distortion, magnification, and object size. In radiography, the anatomical part can be measured on the image. This is known as the image size. Okay, so so we can measure the size of the part of the part that's represented on the image. Okay, and we call that image size. The SID is known. We know what the SID is, and the OID of the anatomical part in the body can be estimated, or it could be roughly measured. Okay, so we can gather the image size, we can gather the SID, and we can gather the OID. With these, the actual image size can be found. Okay, so we can the actual object size. So we can find the actual size of the object just based on knowing these factors that were at play when it was taken, and then measuring the image. Okay, and the relationship is seen here. So we have the magnification factor equals image size over object size. Okay, so image size over object size, and that's going to equal the SID divided by the SOD. Okay, and that's the magnification factor, SID over SOD, right? So we have the SID. If we know the OID, we can find the SOD. All right, and we can measure the image size. Okay, so then we can find the actual object size. Moving on, distortion and shape. So we talked about the size distortion with magnification there. So we can go ahead and we can talk about shape. Shape distortion occurs because of poor tube-part detector alignment. Okay. If the tube is angled, the central ray is not perpendicular. So if this is the IR here, like this, and the central ray is not perpendicular, coming down straight like this with the IR, okay, then shape distortion can occur. Sometimes we angle on purpose, okay, of course we know we put certain angles on the tube, okay, to represent anatomy that would be obscured by other structures, okay, so we throw anatomy off of other structures, all right. If the patient's part is not parallel with the plane of the detector, okay, so the patient's part's here, the detector's here, okay, so parallel two lines together. With the plane of the detector, shape distortion can also occur, okay, so it's not just the central ray being here, it's also the way the patient's positioned, and if a part is represented in an unexpected fashion, this can make diagnosing difficult, okay. So the other thing that can happen is if the not only is the patient just off of the plane of the IR, but the IR can also be angled. Okay, so the IR can also be one side could be farther down, even though the patient is like parallel is with the CR, with the central ray and everything. Okay, if the detector is angled, it's also going to be a misrepresentation. Okay, this can also be called geometric distortion. Okay, for maybe obvious reasons, okay, because we're kind of dealing with the geometry of the way the part in the detector and the tube line up with each other. Distortion of the shape. So shape distortion on the image can be visualized as foreshortening or elongating the part. So the way that the shape distortion can come out on the film is it can be elongated. So this is elongation of the scapula here. Okay, it's not well represented, okay, especially down here. Foreshortening, where it's shown shorter, okay, than it actually is, and then this would be like a true view. Okay, so this is the way it should look. So we can see the difference between these three. This is elongating and foreshortening. So there's some questions on distortion. All right. And go ahead and pause the video here. You can answer these. The answers will be at the end of the video. Okay. Okay, so far we have discussed the factors that go into the sharpness of the image. Now we're going to learn about the visualization factors of the image, okay, or visibility of the image. The first aspect we'll talk about is brightness. The brightness of an image is the overall lightness or darkness on an image. Brightness of an image can be called the density of the image also. This may be a term that's used, but the term is better saved for like film imaging. So texts that have been around a while, you may see density. It's not necessarily incorrect, but it's just better used for film imaging than digital. If the image is too light or dark, it can be difficult to diagnose the patient. So we need the correct amount of brightness on the image. It's the duty of the radiographers to ensure that the brightness of the radiograph is sufficient for the radiologist interpretation, and we have some examples here with our buddy Mr. Rankin. All right, this one here is obviously too dark. Okay, this would be a well-represented image. So this one here is obviously too dark. We can't see much detail in his beard. Okay, in his hair. All this is kind of flat here, okay, where we can see some more detail in here. All right, so this could make it difficult to be represented. This one here is really light, okay, so this is a really light image. All right, even though maybe we can see some detail here. All right, now we couldn't see before here. We can't see any detail in the face. All right, and all that. So this is pretty obvious, right? We need a nice brightness on the image, okay, without it being too bright or too dark. Brightness and technique. Okay, so now we know that we need a nice level of brightness for the image to be diagnosed. How are we going to achieve that? As mass is increased, the X-ray exposure to the IR will be increased proportionally. Okay, we learned that before. So about the emission spectrum of X-rays, as so if we double the mass, the amount of exposure to the IR, the amount of X-rays produced, the amount of X-rays that's going to reach the IR is going to double as well. If the mass is insufficient, the image will be underexposed. If the mass is excessive, the image will be overexposed. So for us, an overexposed image, okay, where there's too much mass, is going to be too dark. Okay, underexposed image is going to be too white. Okay. While the system is automatically programmed to recommend a mass, the radiographer is in control of the selection. Okay, so it's ultimately our responsibility as techs, as radiographers, to select the correct exposure. So now that we talked about brightness and what it represents and how to control it, we'll go ahead and we'll move on to contrast. Contrast is the difference in between adjacent levels of brightness on an image. If the difference in the brightness levels is large, the image is said to have high contrast. So if there's a large difference in the brightness, the image will be said to have high contrast. A high contrast image will have a few shades of brightness leading from the white to the black. Okay, so the very white to the black, there's very few shades of brightness, or in a high contrast image, and we would say that's with less steps. Okay, is where we go from the white to the black. High contrast is also referred to as short scale, as it doesn't take many levels. Okay, so it doesn't take many steps when there's large differences. Okay, in the brightness levels of every step. It doesn't take many to go all the way from the white to the black. Okay, and it can be represented here. Okay, so we have white, we have some grays in here, and then we have different blacks. They all looks black to us, but there's different levels of black in here, just like the white. Okay, so this could be called short scale, is high contrast. If the difference in brightness levels is small, so there's a small difference in all the different brightness levels, the image is said to have low contrast. A low contrast image will have many shades of brightness leading from white to black with more steps. Okay, so there'll be many more steps with a low contrast image than with a high contrast image. Low contrast is also referred to as long scale, as it takes many levels to go from the white to the black. Okay, and that can be seen here. Okay, so we have white, we have many grays, many different ones of grays. We get to darker grays, darker grays, darker grays, darker grays, and then we're into the blacks. Okay, well, what we would view as being black. Okay, it's just darker grays. Okay, and white's just lighter grays, right? But we would call them white and black, right? So we'll go ahead and we'll continue talking about contrast. The number of different brightness levels a system is capable of displaying is the bit depth of the system. The number of levels that the system can represent is 2 to the bit depth of the system. Okay, so we So we raise the bit depth of the so we take 2 and we raise it to the bit depth of the system, okay, to find how many different levels, brightness levels the system is capable of displaying. All right, an example is a system with a bit depth of 10 is capable of displaying 2 to the 10, which is 1024 different brightness levels, okay? This indicates that the number of different grays that the system that can be displayed in every pixel is 1024. So each pixel, which we already have a matrix here, each pixel can represent 1024 different grays. So each pixel will get assigned a value, okay, and that's just going to relate to a gray. Okay, it may look more white, it may look more black, but it's just a gray level, okay? And each pixel can have a different value, okay? And it can be typically 0, okay, to 1023, okay, if the bit depth of this system is 10. All right, 0 is a value, so that's where the extra 1 comes in. All right, and so it can be, this one could be 0, this one could be 500, this one could be 23, this one could be 1023. Okay, so each one can have a different value, each pixel. All the available bit depth is not necessary for displaying the final image. So there's the grayscale. So the grayscale of the image is the number of grays that are actually represented on the final image. Okay, so the system has a certain bit depth, okay, which will always be larger than what the grayscale on the final image is. The processing stages that go into creating the grayscale of the image won't be discussed here. There will be lessons in the Principles of Radiographic 2 playlist, okay, that will discuss this. All right. It's important to note that the human eye can only distinguish about 30 different shades of gray. Okay, so that's one reason why we don't need all the available bit depth, okay, and we can just do the grayscale, but more will be discussed, okay, in Principles of Radiographic Exposure 2 lectures. We'll continue with contrast. When an X-ray photon is transmitted to the IR, okay, it creates a blackness on that part of the image. So the more X-rays that's transmitted to a part of the image receptor, it's going to make that area more and more black. Okay. When an X-ray photon is absorbed in the body, it creates a whiteness on that part of the image. Okay, so when the X-ray photon gets absorbed inside the body, it creates more and more whiteness on the image. Subject contrast is the degree of differential absorption that occurs through different anatomical structures of the body. Okay, so so there's the concept of contrast of the image, okay, which will be like the final contrast might be like the grayscale that we would say of the image, which could be high and low. There's also subject contrast, which is the degree of differential absorption that occurs throughout the body. So remember, the difference in the transmission and absorption of different tissues is called differential absorption. Okay, so the difference between the transmission and absorption of different tissues is differential absorption. When there is a little difference within the part being x-rayed, the subject contrast is low. Okay, so when there's little difference in within the part, okay, so there's very little difference in the differential absorption of the parts being x-rayed, the subject contrast is said to be low. When there is a greater difference within the part being x-rayed, the subject contrast is high. Okay, so the subject contrast is like the contrast of the part, okay, and how differential absorption occurs through that part differently. Okay, so an abdomen is like a low contrast area because the organs, the muscle, and all that has close densities and Z numbers and all that. So it's a low contrast area part. The chest is high because it has bone and you have lung, okay, and you have heart, a muscle there. Okay, so from the bone especially to the lung, there's high contrast. There's a big difference in the way differential absorption occurs in those anatomies, okay, in those structures. And we can see here, all right, with this, that as there's four, in this example, there's just 4 x-rays coming into each of these tissues, okay, and air it's all going to be transmitted. Okay, so that's going to create a darkness on the image. Okay, it's going to create a darkness on the image. In fat, more is going to be absorbed, okay, than in air. So it's going to be kind of like in the gray area. And then bone is going to absorb most, if not all. You know, it's going to absorb a gray amount here, all but one, and it's going to make that area white on the image. We'll go ahead and we'll talk about contrast and technique. So KVP is a primary controller of the subject contrast. As KVP increases, penetration of the beam will increase. Okay, it's more energetic, as we learned before, and it's gonna more of the beam is gonna penetrate the body. Okay, and the differences in attenuation will be decreased. Okay, of the tissues that were X-raying. Therefore, contrast will be lowered. So it'll be lower contrast as KVP increases. As KVP decreases, penetration of the beam will decrease, and the differences in attenuation will be increased. Okay, therefore contrast will be higher. So let's talk about KVP and contrast. So when we use low KVP, similar tissues will absorb the beam differently. So if the tissues are similar, it's going to absorb the beam differently. And remember the difference in the absorption. The difference of absorption is what's going to make the black and the whites on the image. Okay, so if something like fat and muscle, which are very close together, fat's the total absorption of fat is 354K. Soft tissue is 405K. Okay, so these are pretty similar. But with low KVP, fat muscle may absorb more X-rays than fat, so it's going to be represented much more white, or maybe dramatically more white with a low KVP. So this would be a very short scale. Okay, things are either going to be very, very much white or very much dark. All right, with a high KVP, the different tissues will transmit the beam more the same. All right, so fat is obviously going to transmit, or air is obviously going to transmit the beam, whether it's low KVP or high KVP, it's going to transmit the beam. Fat is going to absorb a very slight bit of the beam, okay, not as much with low KVP. So it's going to be more dark, okay, and then bone will transmit more at a higher KVP. Okay, if we increase the KVP so much, thin bones and stuff will be just completely black. Okay, they'll be burnout, we say, and everything. So so with a high KVP, things are going to be more the same. Okay, so there's going to be more gray, so the gray scale is going to be longer. Okay. So more about KVP and contrast. So in general, like low KVP is going to give a high subject contrast. So the material is either going to absorb it, okay, or it's not. All right. And then a higher KVP is going to give a lower contrast, okay, where it's a longer scale. All right. So some tissue is going to absorb, even with the higher KVP, it's still going to absorb and make a white, and other ones are going to transmit, okay, to a larger degree. We'll go ahead and we'll look at a representation here of the KVP and contrast. So we have three different hands, or the same hand, but taken with three different KVPs. So at 40, we can see that this is very, very dark. Okay, there's either the grays here, and there's darkness, and there's whiteness. Okay, so all this is very, the bones are very white, and even the tissue is very white, and then it's very dark. Okay, so that's a very short scale of contrast at 65, which maybe a more typical value for a hand. We can see that there's some details in here where there's different levels of gray right in here, and there's also, we can see into the bone where there's just a whiteness. Okay, just on the epiphysis, just on right on the outside of the bone, and then inside there's different levels of gray. And then with a higher KVP, we can see that there's even some blackness happening on the thinner parts of the bones. Okay, and we can also see the different muscle structures. Okay, from here to here better represented than even here. Okay, so this is like a longer scale of contrast. Okay, they're still very dark, but there's also white, and there's also more grays in between. Okay, with a higher kVp. Contrast and resolution. Okay, so there's 100% contrast is black and white. All right, so text in a textbook where the background is white, the text is typically black. Okay, will be 100% contrast. Contrast resolution is the ability to anatomical structures of similar subject to represent. Okay, so contrast resolution is the ability to represent anatomical structures of similar subject contrast. Contrast resolution is difficult to quantify because it depends on the human observer as well as the image quality. Okay, so we want to say, hey, this is a quality image, it's got good contrast, but it depends on the human observer. Okay, the human observer can visualize about 30 different shades of gray, as we mentioned before. Contrast resolution is changed with the size of the object. So the smaller the object is, the harder it is to distinguish between the other objects around that might have similar contrast, okay, or like a similar gray level. Okay, so it'll be harder to distinguish a smaller object. This being established in radiology, contrast resolution improves with lower kVps. All right, so the lower kVps we use, the better. We'll go ahead and we'll talk about the spatial resolution, the answers to the questions that were posed earlier. Well, the first question was, the image of a mammography system can resolve objects as small as 1/800th of an inch. What spatial frequency does this represent? So we have the measurement in inches, so we need to watch that. So first we'll convert. Okay, so 1/800th of an inch, there's 25.4 millimeters per inch. All right, so we'll just multiply this together and we get this value. So it's this millimeters is the size of the object can represent, which if we go 1, 2, 3, that's 31.75 micrometers. So that's a reasonable number. Okay, so we can believe that we're doing okay so far. So two objects per line pair. All right, so there are 2 objects can be represented per line pair. So we go ahead and we will multiply this by 2. Okay, so we get this, which is millimeters per line pair now. Okay, so we need to flip that, so we have line pairs per millimeter. All right, and we go ahead and we take this value here, and it becomes out of 15.7 line pairs per millimeter. Okay, so this mammography system is 15.7 line pairs per millimeter. The resolution of a system is 12 line pairs per millimeter. How small of an object can the system resolve is the question. So we have 12 line pairs per millimeter. We know that that a line pair can be 2 objects, right? So we go ahead and we'll take the 12 line pairs, we'll multiply it by 2. That's going to equal 24 objects per millimeter. Okay, we'll inverse that. Okay, so we have millimeters per object then. Objects per millimeter. Now we have millimeters per object. All right, and we get this value, and that's going to represent. That's going to be 41.7 micrometers. Okay, if we just move this decimal point, right? So how small of an object can the system resolve? The system can resolve 41.7 micrometers. Okay. The next question was, what is the spatial resolution of a 512 by 512 CT image, which is the common matrix in CT, that has a field of view of 40 centimeters? So what's the spatial resolution? So one of the first things is that this is in centimeters. We need millimeters for spatial resolutions, line pairs per millimeter. But we also need to find the pixel size. Okay, so we have the field of view, which is 40 centimeters here, and we have the matrix. So we'll go ahead and we'll find the pixel size. Okay, and we have this is in centimeters. All right, we'll convert that to meters. So there's 10 millimeters in every centimeter. So we'll multiply this by 10 and we get this value. So that's millimeters per pixel is what we have here. Okay. It takes 2 pixels to make a line pair. Okay, so we know that. So we're going to go ahead and we'll multiply this by 2. So now we have millimeters per line pair, this value, and then we'll inverse that. So we have line pairs per millimeter, and it comes out to this value. So it's 0.64 line pairs per millimeter is the resolution of this CT system with this field of view. So we'll go ahead and we'll explore the distortion answers. The first question that was posed was a chest x-ray is taken with the source of 90 centimeters away from the IR and the heart is 8 centimeters away from the IR. Okay, so we know that the 8 centimeters is going to be the OID. Alright, and we know we need SID over SOD. So we can find the SOD by taking the SID and subtracting it from the OID. What is the magnification factor of the heart in this radiograph? Okay, so we can go ahead and we can just plug that in. We can find the SOD just right here in the equation if we're comfortable with doing that. We get 90, which will be over 82. Okay, and that's going to come out to 1.098 for the magnification factor for this question. The second question poses that the image size of the thoracic body on the lateral view is 6 centimeters. The SID is 72 inches. If the vertebral body is 8 inches away from the IR, what is the actual size of the vertebral body? Okay, so we got to notice here that we have 6 centimeters. Okay, and the rest are in inches, so we need to convert this. We'll probably just convert everything to inches, right? But we can convert these to centimeters too. The image size of the thoracic vertebra. So we're looking for the actual size of the vertebral body. So we're looking for the object size. So we know that SID over SOD equals image size over object size. So we'll go ahead, we'll go back to that, and we'll set this up right here. Okay, and we'll plug that in. All right. We know it's 8 inches away. So we'll go ahead and we'll set it up just like we did for the SID and SOD. Here we need to convert the centimeters to inches. So we're going to divide by 2.54, okay, to convert the inches. All right, and we have the object size. We know we need to cross multiply, so we'll cross multiply this. We can solve this, we can solve this, and we can cross multiply here. When we do that, this is the 64. This is a 2.362 roughly that comes down here, okay. And then we can multiply these two together to get the 151, okay? And we can divide by 72. So we divide by 72, and that's going to isolate the object size, okay? So we go ahead and we do that. We figure what this out is, and we figure it's 2.099 inches. All right. So does this make sense? So, so we found out that the image size by doing this right here, right, in inches is 2.3. Okay, and the object size is 2.0. We know there's always a magnification factor. Okay, so the magnification factor is always going to make the image larger. Okay, the image size is always going to be larger than the object size. Okay, the image size is 2.3, the object size is 2.0. So we can feel pretty confident that these that we've done this correctly. Okay, and it makes sense based on how far away it is and everything. All right. This next question, we had a image that was given, okay, and it says, what type of misrepresentation will be represented on the image with the tube patient detector alignment? Okay, so we have the patient is misaligned here. Okay, so this would be like the patient part. All right, the tube was perpendicular, the IR wasn't misrepresented. All right, so if we go ahead and we represent this brown, which is this brown that we can see, this is the actual object size, okay? It's just brought down, copied and brought down. There's a little bit here that might be difficult to see, but there's here, okay? What's actually going to be shown on the image, okay, it's going to be in this black, okay? So this is going to be foreshortened here, okay? So this is going to look shorter, all right, than what the actual object is, okay? So this is a example of foreshortening, okay, with the patient being misaligned. Radiographic image properties, we'll go ahead and we'll, in order for a radiograph to be of diagnostic quality, it must be sharp, and able to be visualized. Okay, so both of these, the sharpness and the visualization, need to go together. Example, if the image has good contrast, however the anatomy of interest is excessively blurred due to magnification, the exposure will need to be repeated, right? So on a good quality radiograph, we need to have sharpness and visualization. The same with poor brightness, contrast, or geometric distortions due to poor technique or positioning. Okay, so we need to have good technique and we need to have good positioning to reduce magnification, reduce shape distortion, to have good brightness and contrast on the image. Okay. Other factors can play a role into making a good image. Okay, and sharpness and contrast and all that, and we'll explore that in our next video on secondary factors. Okay, we have an example though of what we're talking about here of high spatial resolution, okay, but low visibility. So this is like a low contrast, it's too gray through here, okay, so it's hard to see what we need to see. Here we have low spatial resolution and low visibility, okay, and we have high spatial resolution and high visibility. So this is a good radiograph, okay, we can see what we need, where these other ones aren't well visualized, okay. And as I said, we'll go ahead and we'll, in the next video, we'll explore secondary factors, okay, that go into radiographic image production.